Hi, this is another video about chemical thermodynamics, and in this video we're going to explore something called entropy. So I just wanted to review that the first law of thermodynamics states that energy cannot be created or destroyed. You can change it from one form to another. And to review that enthalpy, which is an capital H, is the amount of heat given off or absorbed under a constant pressure. And these capital D's in this PowerPoint is supposed to be a delta for delta H. Well, we're going to talk about something called a spontaneous process. And I think this is really important in chemistry. A spontaneous reaction is one that will happen without any outside intervention. And so wouldn't it be nice if you know that this equation that you're writing on paper or this reaction that you're going to do in class will actually happen without any outside intervention. Now, spontaneous doesn't mean that it's going to be fast. Rates of reactions are a branch of chemistry called kinetics that we'll be exploring very soon. But spontaneous just means that it is going to happen. So, if a reaction is spontaneous in the forward direction, then it will not be spontaneous in the opposite direction. So, I like to think about a waterfall that's running downhill. Okay, that happens spontaneously, but to have the water go from the ground back up to the top of the waterfall, that's not going to happen spontaneously. Likewise, in a chemical reaction, if you put sodium metal into water, we'll have a single replacement reaction, getting sodium hydroxide and hydrogen gas, and that's going to happen very violently. But the reverse reaction doesn't happen at all. So let's talk about spontaneity and enthalpy. Sometimes an exothermic reaction is spontaneous. As a matter of fact, a negative delta H is what we call thermodynamically favorable. Another thing we like to say is that's a driving force, or it's something that will help the reaction produce products. So for instance, when we combust methane, so it would be CH4 plus O2 yields CO2 in water, the delta H is negative 890 kilojoules. That is exothermic and it's spontaneous. It happens. Acid-base neutralizations, again, a delta H for an example of one of these reactions is negative. It's exothermic and it is spontaneous. But we can't just say that, only exothermic reactions are spontaneous, because here we have ice melting and that's a phase change, but the delta H is a positive 6 kilojoules. So what the conclusion is that the sign of delta H is not enough to determine if something is spontaneous or not. Negative delta H is favorable, but it doesn't mean that the reaction is going to happen. So we need something else to determine spontaneity, and it's called entropy. This is a thermodynamic quantity, and it's a measure of the randomness or the disorder of a system. Entropy has the symbol capital S, and the greater something is disordered, or the more randomness there is, then you'll have a larger value for S. If you have something that's very ordered, like say a solid, it would have a smaller value for S. Now the units are different from enthalpy. Enthalpies are reported as kilojoules, but just take note here that the entropies for, the units for entropies are joules per mole Kelvin. So for any substance, it should make sense that the entropy of a solid will be the lowest, and then the entropy of the gas will be the highest, because gases have a lot more randomness and disorder. So entropy is a state function, just like enthalpy. So delta S is going to be final entropy minus initial. And remember that a state function, it depends only on where you start and where you end. It doesn't depend on the pathway. And entropy is going to have three parts. So you're going to have a number, you're going to have that unit, which is going to be joules, and you're going to have a sign. It can be positive or it can be negative, and that's very important. So let's go ahead and predict the sign of delta S in these reactions. Here we go. Okay, so solid, gas, solid. I like to look at which side has the highest disorder. And so in looking at this side, our reactant side, has more disorder, and I box it in. And the reason it has more disorder is because there's a mole of gas here. Over here, there's only solid. Okay, so I just boxed in the side with more disorder. So delta S is going to be products minus a bigger number, reactants. So this delta S is going to be negative. All right, let's look here. We have 1 mole of gas plus 3 moles of gas. That is 4 moles of gas, and it's yielding 2 moles of ammonia gas. Again, our reactant side, because it has more moles of gas than the product side, has the greater disorder. And so here again, delta S is going to be negative. Again, this would be a smaller number minus a bigger number, so it would be negative. Here we have a solid, and aqueous ions in solution are more disordered than a solid. So here our product side has greater disorder. So this is a higher number minus that number. So here our delta S is going to be positive. And here we have a solid going to a liquid, and liquids are more disordered. And so here the sign of delta S will be positive. Okay, so the second law of thermodynamics states that in any spontaneous process, there is always an increase in the entropy of the universe. So what that means is that if you have a positive S, a positive entropy, that is favorable for a spontaneous reaction, but we also have to remember that we have to take into account the enthalpy as well. All right, how do we calculate entropy changes? Well, we already know, believe it or not, because we calculated enthalpy changes, and it's exactly the same. So what it is delta S, see if this looks familiar, of a reaction is equal to the sum, don't forget the coefficient, of the entropies of the products minus the sum, don't forget your coefficient, of the entropies of the reactants. And again, we have tables where we can look up the entropies of just about everything imaginable. So here we have nitrogen, and N2, the enthalpy of formation would have been 0, but the entropy is not 0. That nitrogen gas has an entropy of 192 joules per Kelvin mole. Hydrogen has an entropy of 131 joules per Kelvin mole, and here's ammonia. So I would like for you to go ahead and calculate the delta S for this reaction. So you can stop the video and go ahead and calculate that, and we'll see if you get it right tomorrow. Okay, so let's summarize. If a reaction produces more gas molecules than it consumes, then our delta S would be positive. If the total number of gas molecules goes down, so our system is becoming more ordered, then if it's becoming more ordered, we're going to have a smaller entropy minus a larger entropy, and so our delta S will be negative. And if there's no net change in the total number of gas molecules, then, what is the entropy? Well, we're going to have to calculate it to find out. It's going to be close to 0. All right, so the last thing is our third law of thermodynamics, and that states that the entropy of a pure crystalline substance is 0 at the temperature of absolute 0, which is 0 Kelvin. So we have 0 entropies when it's a pure, completely organized crystal at absolute 0.